my final story has to do with the star Proxima Centauri. And a few months ago, a big news story that came out was the observations of a planet that was observed around Proxima Centauri. And Proxima Centauri is exciting because it's the closest star to us, to the Sun. It's located just over 4 light years away. And Proxima Centauri is part of what we think is part of the Alpha Centauri system. So there's Alpha Centauri A and B, which are 2 stars that are very close together. But Proxima Centauri is actually much further away. I mean, it's only about 1/4 of a light year further away than Alpha Centauri. But because both Alpha and Proxima Centauri are so close to us relative to everything else in the sky, this separation between Alpha Centauri A and B and Proxima Centauri is over 2 degrees, which is over 4 times the width of the full moon. And so this is actually one reason why Proxima Centauri wasn't actually discovered until just over 100 years ago. Oh, before I go into that, here is just a size comparison of our Sun and plus Alpha Centauri A and Alpha Centauri B. So both Alpha Centauri A and B are pretty close to the Sun's size. One is slightly smaller, the other is slightly larger. But Proxima Centauri is a much, much smaller star. It's about only about 1/10 the mass of the Sun, and it's much, much dimmer, which is why it took so long for people to find it. And as I said, it was discovered just over 100 years ago. And even when after it was discovered, people weren't sure whether they were actually gravitationally bound, meaning whether Proxima Centauri was in orbit around Alpha Centauri A and B. And there was some evidence that it was. One is that they're relatively close, so close in the sense that they were about 2 degrees apart in the sky. But this is the paper where the discovery of Proxima Centauri was made. So it was discovered in 1915 at an observatory in South Africa. And the other important piece of evidence to suggest that they are related is that they have the same motions in the sky. So all stars in our galaxy are in orbit around the galaxy, but for the most part, stars are so far away that it's very difficult to actually see their motions. But because Alpha Centauri and Proxima Centauri are so close to us, we can actually measure what we call the proper motions, meaning the amount of motion that they have against much further background stars. And so here is a paper from 1928 where the author looks at the proper motions in 2 different coordinates for Alpha Centauri A and B and Proxima Centauri. So you can see that the motions are relatively close, especially the motions in the right ascension direction. And so it's really this indirect evidence, the proximity and their motions that suggest that these 3 stars are associated with each other. And part of the problem is that Proxima Centauri, I mean, another measurement that you could have made is the velocity that the star is moving either towards us or away from us. And that's what's known as the Doppler Velocity. And you have to observe the light from the star very carefully through a spectrograph. But the problem with Proxima Centauri is that even though it's so close, it's such a faint star that it was very difficult to get enough light to do a proper spectrographic measurement. But that's all changed just because we have this new generation of instruments that have been developed to find planets around stars, and those have allowed us to make really careful spectroscopic measurements even for very faint stars. And so again, we go to the European Southern Observatories, in this case, 3.6 meter telescope, the same one that was used along with the same instrument, the HARP spectrograph that was used to find the planet around Proxima Centauri. And the authors, in this case, were able to use that to really carefully measure the velocities of Proxima Centauri and the Alpha Centauri stars. So in this case, they found that Proxima Centauri was moving towards us. So that's what this minus means. A positive number would mean it's moving away from us. So Proxima Centauri is moving at minus 21,700 meters per second. So that means it's moving towards us at about 21 kilometers per second. And Alpha Centauri has very close velocity, just over 22 kilometers per second. It's moving towards us. And notice the errors are relatively small, 4 meters per second. So that's basically a walking or bicycling speed. Whereas here, Proxima Centauri has much larger error bar, and that has to do, again, with how faint it is. So even with this powerful spectrograph, they still have a slightly larger, or an error that's about 9 times larger or 7 times larger than Alpha Centauri's. But this isn't the full story, because there are, when you're measuring velocities at this level of accuracy, you have to deal with other effects that can swamp it, that measurement. So it turns out that there's something known as convective blueshift that is important, and it has to do with the fact that when you look at stars, or low mass stars like the Sun, Alpha Centauri and Proxima Centauri, their surface isn't uniform, but they have these convective cells, these regions where the stellar surface is boiling. And so the center of these cells, material is actually coming up from the interior of the star. And so this region is brighter and hotter, and as it cools off, the gas falls back down along these darker edges to the cell. So this is these convective cells have been observed for the Sun, and because this material is coming up, it will lead to a blue shift in the light, meaning it'll appear as if that gas is moving towards you. And for the Sun, this is adds on the order of about 300 meters per second to the velocity that we see from the Sun. So that has to be corrected for in Alpha Centauri A and B. And then it turns out that the authors of this paper investigated, and they determined that they can correct for Alpha Centauri, but it turns out that this particular effect isn't as important for Proxima Centauri, so they ignore it. But this is something that they worried about. Another thing that they worried about is gravitational redshift. So when light is emitted from the surface of a star, it has to climb up out of the gravity well. And from Einstein's general relativity, theory of general relativity, we know that as it climbs out, it loses energy slightly, and so it causes the wavelength to lengthen or to become longer. And so this, again, is an effect that's important enough that they have to account for this. And so this effect has to do with not only the amount of, basically the amount of gravity at the star surface. And so it has to do with how much mass there is in that star, but also how close that surface is to the center of the star. And so in both Proxima and Alpha Centauri's case, they have to correct on the order of about 500 meters per second for this particular effect. All right, so after making these corrections, what they find is that it is, in fact, based on the relative velocities of these stars, their motions both towards us as well as the motions in the sky, so perpendicular to that radial motion, they find that Proxima Centauri is likely to be in orbit around Alpha Centauri. And this orbit is just under 600,000 years. So these points show where Proxima Centauri is every 40,000 years. So this is where it will be in the sky every 40,000 years in the future. And this orbit isn't circular, it's elliptical, meaning it actually gets as close as 4,300 astronomical units, as well as far as 13,000 astronomical units away from Alpha Centauri. All right, so with that, I'm going to turn it over to Steve, And I'll be happy to answer questions about these stories at the end.